The Ben Heck Show is brought to you by Element 14, the electronic design community where you can connect and collaborate with top engineers from around the world. Join now at element14.com. Hello and welcome back to the Ben Heck Show. In 2014, we created a project based off the classic British computer, the ZX Spectrum, or as they say in some vernaculars, ZX Spectrum. What we did was we hand-wired a duplicate of it from scratch using breadboards that had the same functionality as the original computer. You could load tapes onto it, you could play games, it had a built-in keyboard, everything. Well, that was a really fun project, and I've kind of wanted to make a better version of it, something that other people could create as well. So in this series of episodes, we're going to come back to this, but do it right. Here's how. We're going to recreate the schematic for the ZX Spectrum, or I said ZX, in Eagle. Then we're going to design a small PCB for it, hopefully as close as possible to our original unit, although it might be slightly larger just because we have to actually properly run traces instead of piling wires everywhere. Then we will create a new portable unit based off of our PCB. I want to keep some of the same curves and shape of this, so I want it to look more like the original unit than what we built in 2014. Then we can make the files available online at element14.com so you can spin your own boards and try it yourself. Let's get started.
Amazing hacks.
How can we make this portable?
Inspired designs.
I am the internet troll.
Regrettable acting.
Batten down the hatches!
Each week, Element 14's The Ben Heck Show brings you innovative projects using electronics, engineering, and more.
Let's take a look at the block diagram of the ZX Spectrum. The ULA, uncommitted logic array, is a custom chip that they made to do the video, keyboard matrixing, and other things. It actually drives the Z80, so this thing will send the clocks to make this execute. The reason for that is because if the ULA is using this RAM in order to draw the screen, it doesn't want the CPU to try to access it at the same time. The CPU and the ULA are connected through a pair of 4-bit multiplexers that allows the CPU's address lines to be channeled into the RAM and again controlled by the ULA. The CPU has direct access to 16K ROM at the bottom of memory, that's where it boots. That contains the BIOS and the BASIC. There's also a 32K RAM on the upper half of memory. The Z80 has that all to itself. It is not governed by the ULA in that situation. And also the ULA is connected to analog circuitry, which is what actually drives a screen. Okay, let's make some custom parts in Eagle. I'm going to create a library just for the ZX Spectrum. So we go to the control panel and we go to library, new. Okay, so this is our new library here. What we can do is we can copy existing parts and make them work for our library. The most important of which is the ULA, the custom chip in the Spectrum. It's a DIP40. So what I can do is copy an existing DIP40 chip and then modify it for our purposes. So I'm going to go back to the control panel and I'm going to open up libraries and, oh, here we go. Here's a DIP40 Z80, perfect. Okay, so I'm going to right click on this and go copy to library, and it will copy it to the library that is already open on my screen. Okay, there it is. There is a DIP40, the classic shape, the smooth, crisp texture. All right, so let's go to the symbol. So we're going to draw something that represents the chip. We want to keep this in the center because that's going to be used for the schematic. That might not be perfect, but oh well. Okay, let's get some pins. All right, well, there's 40 of them, so I'm just going to put in 40. 1, 2, 3, 4, 5, 6, 7. That's a fairly literal representation of our chip, but I don't mind. And every time I click one of these, it's going to auto increment the number, so I don't want to go from 20 up here because that would be incorrect. I go 20, 21, and then go up, just like a normal integrated circuit would be labeled, and this will end at 40. Okay, there are all the connections. Now I'm going to label them, and I will label them based off of the schematic I found for the ZX Spectrum. Okay, here is the schematic view of the ULA. I did actually end up grouping things a little bit. We have our RAM axis up here, data lines in the lower right, keyboard on the upper right, and our interrupt requests and analog on the lower left. So what I'm going to do now is hit the device view, and device is where you actually combine the schematic with the physical device footprint. And we grabbed the Z80 footprint, so I already have that. So now we just have to assign the pins. So we're going to create a new device, which is the ZX ULA. We can hit OK. Now we're in device view. So this shows us the schematic and the physical layout. We have to connect things, so we're going to go down to connect. All right, so this is the boring part. We have to go through one by one and double check that the name of the signal is hooked up to the appropriate pad. So for instance, pin 1 is the column address strobe line, which is that. So you click on it and then you hit connect. Then 2 is the right, and we click on that and we hit connect. Okay, we do this for all 40. The other non-standard part on the ZX Spectrum is the LM1889 TV video modulator. This is a new old stock item. This actually takes the YUV signals off of the ULA and turns it into a video signal that you can see on a television. It'll actually be PAL, but most modern LCDs can run PAL. So I've created another part for this. Again, I have all the custom pins here. This is actually a DIP 18. And yeah, I've connected everything together. So now we can use these custom parts in our circuit. Everything else should be off the shelf and have parts in Eagle already, such as these flip-flops, ROM, surface mount, and our RAM. With my custom parts created, I can start the schematic. I'm gonna go to New, Schematic. Since I created some new libraries, I need to actually manually use them. Okay, so it's the ZX Spectrum library. All right, so now I can open that when I go to my library icon here. So that's something to remember. If you create a new library or add a new library to your computer, you need to use it before you can actually select it over here. All right, so here's the two parts that I made. Let's start with the ZX Zula. It looks like it's like a character from like an 80s movie. Like, what was that movie? Crawl or something? Okay, there's our ULA. Let's also get the analog chip. The analog chip looks bigger than the ULA. Nice one, Ben. It's just scaled differently. Okay, let's see, what else do we need? Where is my schematic? Well, this looks like a nice original crusty schematic here. Later issues of the ZX Spectrum had an additional logic chip for some of the decoding and multiplexing. I'm just going to create that using 7.4 series logic and some multiplexers. Okay, so we also need a Z80, the classic CPU. I believe there is one in, oh yeah, here we go, Zilog Z80 CPU, look at that, it's still in this. Beauty! The Z80 is actually still used today and still manufactured. Oh yeah, look at all those juicy signals. Oh yeah. All right, we need some RAM. So I'm actually using the same manufacturer of RAM as the previous ZX project. Here's a fun game during this episode. Count every time I say Z instead of Z by accident. I'm turning British. Ah! All right, let's look for some SRAM, which is static RAM. So back in the old 8-bit computer days, they had dynamic RAM usually instead of static RAM. It was cheaper. It used a capacitor for every bit. However, it needed to be refreshed about every 5 milliseconds, else the capacitors would discharge. The thing that was great about the Z80 was it had a built-in refresh circuit, so it would do that for you automatically. We're going to use a static RAM, which uses flip-flops. It takes a larger die area, so it would have been prohibitively expensive back in the early 80s, but nowadays, who cares? Oh, here we go. 256K bits, which is 32 kilobytes. CMOS static RAM. All right, let's find, okay, we don't want a DIP package. I want to try to do this with as much surface mount as possible. I believe that's the correct RAM. There we go. Okay, so we need two of these. We need one for the CPU, and then we need another one for the video memory. Now these are 32K RAMs. The video memory is only 16K, so the upper 16K of this RAM will sadly go to waste at a loss of almost $1.50. Here's a fun story. The 32K RAM expansion for the ZX Spectrum actually used faulty 64K RAM chips, and they would use 8 chips that had the same faulty bank, and then you just use the working 32K bank, and that was another way they cut costs. All right, we need a ROM. Okay, so have you ever heard the term EEPROM and EEPROM? So EEPROM is electrically erasable programmable read-only memory, what we probably call flash now. EEPROM, only one E, is erasable programmable read-only memory, which is usually the memory that has a window in it. We have these one-time programmable memories here from, I think they're Atmel. So even though they don't have an erasable window, they'll still be considered an EEPROM. All right, this one should work. It's a PLCC-32 socketed ROM. And this is kind of a hack. This is meant to go into it's meant to go into a socket like this. But I think we can gain a little space by programming it with a adapter like this, and then just surface mount soldering it into our board. It's kind of a hack, but it'll gain us some space. All right, so we've got our ROM. Okay, now we need a flip-flop, and not the kinds you wear. So it's gonna be a 574 series flip-flop. There's the part. Okay. All right, there's a flip-flop. And now I need to find the multiplexer. There we go. That's a 2-to-1. Okay, these should be the main parts that I need. You got the RAM, the CPU, the ROM, the flip-flop to connect between the video RAM and the ULA, and a multiplexer to connect between the CPU and the ULA. I've wired together the logic for the ZX Spectrum. Let's take a look. Here's the Z80. Its address line connects directly to the 32K RAM. There's also a data bus here with pull-ups. And the Z80 also connects directly to the ROM. There's going to be a switch so we can select the top or bottom half of the 32K ROM to select either the original BIOS or the new Gosh Wonderful BIOS, which we also used in our project in 2014. Here is the multiplexer. This allows us to convert the 14 address signals into a row column signal that is compatible with older memory. We're not using older memory, but we need to convert the ULA's older style memory signals into newer memory. So we use the multiplexer for one part of that, and the other part of that is done with this flip-flop. Basically, we cycle which half of the bus is going to the RAM, so the ULA thinks it's talking to ancient memory from the 80s. Here's the ULA's RAM. Again, it's 32K. We're only using the bottom 16K, so we actually pull a 14 low right there. Here's the ULA that we designed. Connects to the bus in a pretty straightforward way. Here's the power supply section for it. Over here is the, there's a couple transistors here that drive the clock. So the ULA actually drives the clock of the CPU. So it can pause the CPU when the CPU is trying to access the memory it's trying to access, basically to avoid memory contention. There's also a simple circuit to drive the speaker, which is connected to the microphone and the ear jack. All three of those things go to one line, the cassette speaker line. And that's a pretty old analog circuit. It's meant for ancient tape decks, so I don't know if it'll work with modern stuff. And the idea is you can hook this up to a tablet, or heck, you could even plug it into your computer and run YouTube videos of people loading Spectrum games, and in theory it should load, but we'll have to see. Okay, this drives the I/O request line. That was actually late bodge that the early systems didn't have, but they needed. So I actually used the Series 6 schematics and the Series 2 schematics and combined them. This part I'm a little worried about. This is all the analog circuitry that works along with the video decoder chip to create a signal. There's a lot of little resistors there, and I hope I have the right types of transistors and everything. I'm using 0805 size surface mount for everything, so it's consistent. And down here, this is the final video amplification circuit that goes to the screen. This is an enlarged portion of the schematic. I turned it into a single page PDF. This is the analog circuit. It looks like there's quite a few things here, but it's actually not too bad. So what I'm gonna do is one by one, put these into my schematic, and as I go, I'm going to mark them off with a highlighter to make sure everything's there. Okay, it looks like I have every passive component for the analog video circuit drawn into my schematic. Now it's time to work on the keyboard. Let's put the keyboard into the schematic. Here's how it worked. The ULA had 5 pins, which were the column drivers for a keyboard, and see how it's actually split like this? So you've got 5 here and 5 here. For the other half of the matrix, they actually use the top half of the address bus. So the CPU would actually assert the top 8 bits in a certain pattern in order to check the keys. So for instance, these would be all 1, but A15 would have a 0 on it, and then it would see if any of these were pulled down to 0, and then it would know that key was pressed. Likewise, if it wanted to check A11, it would make all of these 1 except for A11, which would be a 0, and then if any of those appeared as 0s instead of 1s, since they had pull-ups, they would know this key was pressed. And that would actually allow you to sample every key and not need diodes on every key to properly separate them. However, you would have to do 8 reads every cycle in order to get all the key data. But it's a fairly efficient and cheap way of doing it. So we're going to reproduce this in our schematic using a bunch of tact switches, and then we'll attach it to the ULA and the address lines. There isn't a diode on every key, but there is a diode between each one of the column lines and the main address bus, so that pushing buttons during other operations besides key reads won't affect the bus. So you can't push the buttons and affect the data, for instance. I'm going to draw the keyboard into Eagle now. So I have a tact switch that I found in the library, and I'm going to just copy it using the copy tool, which is very handy for, copying things. Boy, this is exciting. I never thought my life would be this exciting when I grew up, until I grew up and then realized my life would be this exciting. I can copy a whole group at once? It's a revelation. All right, so I'm going to connect the rows first, so let's do this. And the rows are going to go to the address lines. So I'll get them out of here first, so to speak. Everybody everywhere is going to say Clint Eastwood is the biggest yellow belly in the West. I'm going to connect the rows to the address lines here.
I gave away my birthright for $5,000.
Okay, let's add some diodes. See, I'm just going to go find a diode somewhere else and just copy it. Woo! I'm just using some garden variety diodes. And I'm not trying to make my schematic look very pretty. It's not going to win any beauty pageants, but as long as it works, that's all I care about. We don't always have time to make things look pretty on the Ben Heck Show, but they're going to work pretty good. So I'm going to bring these nets up here and just terminate them, and then we'll come back and put a label on. All right, we're going to connect the columns together. And I'm very sloppily going over lines, but as long as you don't end on the line, it's fine. See how that's fine? But if I were to go to the line, it would say, hey, do you want to connect these? And I don't. I've done the schematic for the keyboard. Now I need to attach the signals. All right, so over here, let's attach some labels. Let's see. This goes to A11. This one goes to A11. This one goes to 10. Okay, so there's the address lines. So by putting the diode in this direction, that means the current can flow into these lines, but not the other direction, which will prevent the keys from affecting the bus in a negative fashion. Affecting, not affecting. There's a difference. All right, now I'm going to attach these to the key sections of the ULA, the University of Los Angeles, I guess. All right, so now we have our keyboard ready to go. So this is pretty much the entire schematic. It's not pretty, but it should work. Now comes the real fun, laying out the PCB. Before I get too far with the PCB design, I print it out at actual size, and then I make sure all my components line up to the pads, just to ensure that I have the correct versions of the chips. It looks like everything lines up, so I'm good to continue. Now I'm going to click on the board button to generate a PCB. Oh boy, create from schematic, here we go. Oh no, look at this. Actually, it's arranged fairly neatly. I mean, it still looks like a mess. So I have some basic dimensions for the PCB. 4.125 over and 5.5 inches tall. I'm just dragging the existing line that came with it. All right, now I'm gonna start dragging pieces over. Let's see, let's start with the ULA. Look at that, it's like, ah, doing, ah, doing. I'm just gonna rough this out, just get the basic shapes. I wanna make sure I have the RAMs right. This is the 32K RAM, so this is the one for the CPU. So I'm gonna put it by the CPU. I wanna leave space around the edges of the PCB so there's room to run lots of ground and power. Here is the headphone jack for tape loading. I'll put this down here someplace. What are these? Oh, these are 7.4 series logic. This is used for the memory addressing, so I'm gonna put these down here. There do exist surface mount Z80s. The reason I did not use one is because I have so many DIP 40 Z80s laying around. I have more laying around than I will ever need, so I need to use as many as I can. I think I'm gonna put these are the multiplexers. I'm gonna actually hit the center mouse button to put it to the back of the board, so that can be behind the board under the CPU. That way we can have them closer to the CPU, which is where they need to be, but take up less space. Okay, this crystal here, this 4 point whatever megahertz crystal, that's the PAL color burst crystal. So I'm gonna put that down by the video. I have some headers here for the battery should go down by this. Regulator goes by the switch. There's the 14 megahertz surface mount crystal. This goes into the ULA. I'm trying to keep everything as close as I can. As far as passives, especially filter capacitors, you want them to be as close as possible to their intended device. Right now we have 3 filter capacitors. Probably should add some more. And I'm going to put them close to their intended devices so they can have the best effect. When you look at a data sheet for a product, you'll often see, place this within a certain distance of component with, copper underneath it. They'll give you pretty good instructions of the best placement. I have to make sure I place these switches in the right order. I think I just loaded them in some sort of generic sequence, so I'm going to have to double check that. Then there's quite a few passives. Look at all this. Most of these are used for bus isolation, but there's also pull-ups, pull-downs, and filter capacitors. So I'm going to have to move all of these to the best location on the board. Also, I'm going to want mounting points so this board can attach to things, so I can add things like drill holes, like this. Might want to go back and, let's see, hole. Let's make it fit a size 4 screw. And once I have all the components in the best approximate position, then I'll start to run traces. I might need to move them once I start running traces. I might not realize there's enough clearance. And the reason why I didn't use the full connection on these tack switches here was because I want to make sure we have clearance through them and across them in order to move as many traces as possible. This part's probably going to take me a while, so stay tuned. Oh boy, I'm finally done with the layout. That was a lot of work. Let's take a look. Okay, so here's the Z80, and it shares a bus pretty directly with the ROM and the RAM. Behind the Z80 are the multiplexers. See how they're, between the pins? Very efficient. Then we have our buffer resistors and pull-up resistors here. Most of those are between the Z80 and the ULA. Over on the left, the ULA has a large power rail going through it, and there's a flip-flop and its RAM. A power switch is down near that, since that was really the only place I could put it. The 7.4 series logic here, this is used for addressing the upper RAM. Basically, if A15 is active, that means you're looking at the upper 32K, which means the RAM is active. Here's the final layout of the keyboard. I actually labeled each key 1, 2, 3, 4, 0, enter, space. Just so when we're testing the unit, we can actually type things in and know where everything is. So this is the part I'm still worried about, the analog. We have the TV encoder here, and all the associated analog circuitry is around it, including the audio circuitry. It's kind of tricky when everything's brought into the board. You might not know where things go. Like, you might have a capacitor connected to, VCC and ground, and that capacitor is intended to be near a certain integrated circuit, but you can't really tell. So you need to, keep track of the, capacitor number. This speaker isn't a part. I just put a header here so we can attach it to a small speaker. Then I do a circle which represents the diameter of the speaker I intend to use to make sure there's room for it, which there should be. The reset button to reset everything. The Spectrum didn't have one, but we have one. And over here is the final part of the analog circuit for the video. This is where the video attaches right there. So if I hit rat's nest, it should fill in all the ground planes. There we go. So this is actually what it's going to look like. I'm going to double check the silk screens, make sure everything's there, at least the indicators. I removed a lot of the component numbers and just left their values, just to, give me more space to read things, because there's not a lot of room on this board. Looks like everything's intact. I'm going to send these boards off to Osh Park to get 3 copies back for a great price. In today's episode, we recreated the ZX Spectrum schematics into Eagle and then designed a custom PCB for it. We've sent the boards off to get manufactured, so when we get them back in an upcoming episode, we can install the parts, test and build a new and improved ZX Spectrum portable. That's all the time we have for today. Be sure to check out element14.com/TBHS for more information on other upcoming builds, episodes, and special events. We'll see you next time. Like, are you sure you want to turn off your PlayStation? Yeah, that's probably why I pushed the power button. I made a blow up of, what is this, 1972? And it was, I can't stand my dirty, filthy hippie owner. Ben, you're about to die from super cancer, but the cure will be found in 5 minutes. If only I hadn't wasted time. Very fine, I want to turn off my PlayStation 10. The Ben Heck Show is brought to you by Element 14, the electronic design community where you can connect and collaborate with top engineers from around the world. Join now at element14.com.